Welcome to calculus class. Today we are going to learn two new convergence tests to determine whether a series is converging or diverging. Those tests are called the integral test and the p-series test. The integral test cannot be used on any series. In order to use the integral test, the terms of the series must be positive and decreasing for x values greater than or equal to 1. The function must be continuous for x values greater than or equal to 1. So you must verify that first before using the integral test. Once you have determined that you can use the integral test on the function, the sum from n equals 1 to infinity of a sub n, which is just your series function, and the integral from 1 to infinity of f of x dx, either both converge or both diverge. They do the same thing as each other. So let's take a look at this in practice. For number 1, we're going to be given the sum from n equals 1 to infinity of n over 1 plus n squared. So let's first make sure we can use the integral test here. If I plug in numbers 1 and larger, are all my terms going to be positive? Yes, if I'm subbing in 1, 2, 3, 4, 5, 6, I'm not going to be able to get a negative number out of this. So all of my terms will be positive. Will they be decreasing? Well, you could generate out the first few terms to see if that helps you. But if you consider that the denominator has the same number as the numerator, but we're squaring it and adding 1, that means that the denominator is growing much more rapidly than the numerator, because whatever the numerator is, this one is getting squared and adding 1 on the bottom. So since the denominator is growing more than the numerator, that means that my terms are decreasing for x values greater than or equal to 1. And is this function continuous for x values greater than or equal to 1? Well, I think is it possible that I have a hole in this function or a vertical asymptote? I don't think so, because you have to consider what you know about rational functions. You're going to have a hole if you have a common factor in the numerator and the denominator, and you're going to have a vertical asymptote anytime you don't have a hole and the denominator equals 0. If I set that denominator equal to 0, I would subtract 1 from both sides and I get n squared equals negative 1. The answer to that's an imaginary number. So there are no vertical asymptotes, there are no holes, so this function should be continuous for all x values greater than or equal to 1. So we have determined that we can use the integral test on this problem. Now we are going to apply it. So the way I do that is I'm going to switch this to an integral problem. The integral problem is going to be the integral from 1 to infinity of, notice it says f of x. The series is in terms of the variable n. But my function, I'm going to switch these n's to x's. So it's going to be x over 1 plus x squared. So how, dx. How do I evaluate this integral? Well, this is what's called an improper integral. So I have to calculate a limit as b approaches the problem value of infinity, and then integrate that from 1 to b, x over 1 plus x squared dx. To do that, I'm going to have to use a u substitution where u is my denominator. U equals 1 plus x squared the derivative of u with respect to x is 2x. du equals 2x dx. Multiply by a half on both sides. 1/2 du is equal to x dx. Notice I already have an x in the problem, so I will be able to replace the x dx with 1/2 du. So now I'm going to rewrite my integral problems in terms of u. Whoops, I need my limit in front. Limit as b approaches infinity. The integral from 1 to b, and I'm going to go 1 over u, and then 1/2 du. So I'm going to take that 1/2 in front of my integral symbol. 1/2 integral 1 to b, 1 over u du. And so now what is the integral of 1 over u? That's going to be the natural log of the absolute value of u. And so the limit as b approaches infinity of 1/2 natural log absolute value. Now, I don't want to change the limits of integration, so I'm going to take that u out and go back to 1 plus x squared. And then this will be evaluated from 1 to b. So I'm going to sub in my upper limit. Oops, get this where you can see it good, sorry. And then subtract what I get when I sub in my lower limit of integration. And then I'll evaluate the limit of all of that function as b goes to infinity. So I'll have 1/2 natural log absolute value 1 plus b squared minus 1/2 natural log absolute value 1 plus 1 squared. Okay, so we can simplify that on the right a little bit. The limit as b approaches infinity of 1/2 natural log absolute value 1 plus b squared minus, of course, 1 plus 1 squared is just 1 plus 1, which is 2. So this will be 1/2 natural log of 2, because the absolute value of 2 is 2. So what if I send b to infinity here? Well, infinity squared is infinity, plus 1 is still infinity, the absolute value of infinity is infinity, the natural log of infinity is infinity, and half of infinity is infinity. So you get infinity minus 1/2 natural log of 2, which is infinity take away a constant, which is infinity. So what does this mean? That the improper integral is diverging. And if the improper integral is diverging, then the sum is also diverging by the integral test. So we're going to write, therefore, the series diverges by the integral test. And we're always going to write the test name that we used along with the work that supports that test to support our answer. Okay, number 2. Let's try another one. We're going to do the sum from k equals 1 to infinity of 1 over the quantity 4 plus 2k to the 3/2 power. So let's make sure we can use the integral test before we start applying it. Are the terms going to be positive when our k value here is 1 or greater? Yeah, I'm multiplying, I'm adding, I'm raising to a power. This is in the denominator. There's nothing here that's going to create a negative term. Will the terms decrease as k gets bigger and bigger? Yes, because k is in the denominator, so I'm going to make that denominator grow and grow and grow, which makes the overall value of the fraction get smaller and smaller and smaller. And is the function going to be continuous? Well, there's no common factor in the numerator and the denominator that would create a whole. And if I set my denominator equal to 0 and solve to find any possible vertical asymptotes, well, let's see what that would give us. 4 plus 2k raised to the 3/2 power. If we set that equal to 0, you would do the 2/3 power on both sides, which 2/3 power of 0 is still 0. Subtract 4 on both sides, that's -4. Divide by 2 on both sides, -2. It does have a vertical asymptote, but when k is -2, and here we're saying the function must be continuous for x values greater than or equal to 1. So for any k value that I would have greater than or equal to 1, this thing will be continuous. So I'm cool to use the integral test on this problem. Now I'm going to switch to an integral, and I'm going to do the limit as b approaches infinity of the integral, oh wait, I'll go ahead and write it just as the integral from 1 to infinity before I switch to the limit. 1 over 4 plus 2x raised to the 3/2 power dx. And so I will calculate a limit as b approaches infinity, the integral from 1 to b, 1 over the quantity 4 plus 2x to the 3/2 power dx. So I'm going to have to do a u substitution in order to evaluate this integral. U is going to be equal to 4 plus 2x. The derivative of u with respect to x is equal to 2. So du equals 2 dx. There's not a 2 already in the problem, so 1/2 du is going to equal dx. Now I'm going to rewrite this as a u as my independent variable. So the limit as b approaches infinity of the integral from 1 to b of 1 over u to the 3/2 power times dx is coming out, 1/2 du is going in its place. So now I'm going to pull the 1/2 out in front of my integral and say u to the -3/2 power, so I can use the power rule backwards. So this is going to be the limit as b approaches infinity of, if I add 1 to -3/2, I'm going to get -1/2. So it's going to be u to the -1/2 power. Oh, and I don't want to have my answer be in terms of u. I'm going to go back to the 4 plus 2x to the -1/2 power. Then I'm going to multiply that times the reciprocal of my new power, -2 over 1, which multiplies by the 1/2 that I already had in front of my integral. And this will all be evaluated from 1 to b. So this is going to equal the limit as b approaches infinity. Let's see, 1/2 times -2 is -1, so I'm going to have -1. My negative power is going to kick that down to the denominator, and then it's going to be a positive 1/2 power, which is the same as a square root of 4 plus 2x, and this is evaluated from 1 to b. So now I'm going to take the limit as b approaches, infinity of -1 over the square root of 4 plus 2b minus -1 over the square root of 4 plus 2 times 1. So, if I send my b to infinity, my denominator is going to infinity while my numerator is remaining a constant. So that is going to equal 0. Then it's going to be minus -1, so it's going to be plus. The value of this is a constant, 1 over square root of 6. So that's going to be the answer, 1 over square root of 6. But what does this mean? We're doing a convergence test problem. If the integral converges, which this integral does converge, then that means that the series converges. So I'm going to put therefore the series converges by the integral test. All right. We're going to do one more of these integral test problems. Number 3. The sum from k equals 1 to infinity of 1 over k squared. All right, so we have to check 3 things to use the integral test. The terms of the series must be positive for x values greater than or equal to 1. If I'm plugging in positive numbers, positive integers, squaring them, this is always going to be positive. We also have to make sure that the terms are decreasing. As the k value gets bigger and bigger and bigger, the denominator grows, which makes the overall fraction get smaller. And last, this function has to be continuous for x values greater than or equal to 1. So there is a vertical asymptote when k equals 0, but it only has to be continuous for x values greater than or equal to 1. So it is. All right, we verified what we needed to be able to use the integral test. So now I'm going to rewrite it as an integral from 1 to infinity of 1 over x squared dx. And I'm going to evaluate this integral by taking the limit as b approaches infinity of the integral from 1 to b, and let's call it x to the negative 2 dx. So I'm evaluating this improper integral. If the answer is converging, then the series converges. If the answer is diverging, like going to positive or negative infinity, or the limit does not exist, then we will say that the series is diverging. So we have to do power rule backwards. If I have a power of negative 2 and I add 1 to that, that gives me a new power of negative 1. And the reciprocal of that power is negative 1. Oops, I broke my pencil. And then this is evaluated from 1 to b. So I'm going to substitute in that upper limit of integration. So that's going to be negative 1 over b, because negative 1 times x to the negative 1 power kicks that x down to the denominator, minus negative 1 over 1. Okay, so this is the limit as b approaches infinity of negative 1 over b plus 1. Let's send b to infinity. That means this overall fraction is going to 0. So 0 plus 1 is equal to 1. The improper integral has an answer. Therefore, the series converges by the integral test. All right, now we're going to learn the p-series test. By the way, when you see this printed in a textbook or on an AP exam, that p will be a lowercase italics p. So that's just the way they write it for p-series. So here's what the p-series test says. If a series has the form sum from n equals 1 to infinity of 1 over n to the p power, then when p is greater than 1, the series converges. When p is less than or equal to 1, the series diverges. And there's a special note. Oops, not notes. Okay, here's your special note. Convergence or divergence is unaffected by deleting a finite number of terms from a sequence. And you'll see how that helps us in a moment. Well, no, I'm going to give you an example right now. So, ... If I have the sum from k equals 1 to infinity of 1 over k to the fifth, because my p-value is greater than 1, we would say that this series converges. And if I had the sum from k equals 4 to infinity of 1 over k to the fifth, I have deleted the terms where k is equal to 1, 2, and 3, and I'm just starting at k equals 4. This series also converges. Okay, so if I have to delete a few, it's okay. The series will still converge overall. So let's take a look at example 4. If I have the sum from k equals 1 to infinity of 1 over the square root of k plus 5. I want you to think about what this series looks like. If I substitute in a 1, it's going to be the square root of 1 plus 5, which would be 6 on the bottom. And the second term, if I sub in a 2, is going to be the square root of 2 plus 5, which is 7. And if I sub in a 3, it'll be 1 over the square root of 3 plus 5, which will be 1 over the square root of 8. And if I sub in a 4, it'll be 1 over the square root of 4 plus 5, which is this 1 over the square root of 9. And it's just going to keep going on and on and on. So I want you to consider that another way to write this series is the sum from k equals, let's say we start with 6 and go to infinity, of 1 over the square root of k. And another way to write that is the sum from k equals 6 to infinity of 1 over k to the 1/2 power. Now this looks like a p series, and the p-value is 1/2, which is less than 1. So we would say that this series is diverging. Even though it starts at 6, what we've done is we have deleted a finite number of terms from the sequence at the beginning. So this is okay. So we're going to say there, the p-value is less than 1. Well, less than or equal to 1. So therefore, it diverges by the p-series test. So to support my answer, I'm writing down the p-value and which part of the rule it applies to. I state that it diverges, and I cite this test name by name. All right, this is our last example for today. Number 5, we're going to look at the sum from k equals 1 to infinity of 1 over k cubed. Well, this looks like a p-series to me. What do you think? It has the form 1 over k to the p power. The p-value is equal to 3. So this p-value is greater than 1. So this means that the series, therefore the series converges by the p-series test. And I want you to take a look back before we close at problem 3. We had the sum from 1 to infinity of 1 over k squared. We did this using the integral test, but this was actually a p-series as well. The p-value is 2, which is a number greater than 1. So that means that the series converges by the p-series test. If you notice, that would probably be less work and a shorter, easier way to do that problem. I point that out because I want to emphasize that on many of these problems, you could do them using more than one particular convergence test, but that doesn't mean that you should use any convergence test. You may want to stop and consider the options that you have and which one is shorter and easier, because if you're taking the AP exam, that being a timed test, being able to analyze the quickest way to solve a problem can be advantageous to you. So part of that just comes with practice as well. All right, good luck with your assignment. Please let me know if you have any questions or if you need any help at all. And I hope you have a wonderful day. Bye for now.